Okay guys, the next thing that we're going to look at is the systems with additional poles. So where we stopped off in our last class was where we looked at how a second order system functions, and we did it two examples. The last one was where we had to find the second order characteristics using the pole locations. So this is where we were when we stopped that. We did this problem. Now we need to look and see what happens if a system has more than two poles. So for this purpose, we're going to look at three case studies, and these case studies are provided on page 188. So these are the three case studies that we are taking. So let's look at what are these three case studies all about. So you have the first case study where you have a system with three poles, right? P1, P2, and the third pole is called P3, which is situated at alpha R1. And then in case 2, you will see that you have again P1, P2, and you have P3, but this time it's denoted as alpha R2, right? And in case 3, you see that you have a purely second order system, meaning it has only got two poles, which is P1 and P2. Now, from our studies previously, we found that a second order underdamped system, right, like the one that we have in this diagram here, right, this is a underdamped system. Okay. Now, this is a pure second order system and it is underdamped in nature. Let's look at its characteristics. It's got two poles, and the poles, so this is an underdamped second order system, right? So this is a second order system that we have. And here we see that the poles, that is these two poles that we have, they are having real plus or minus imaginary parts. Okay. Now if you have a look here, our case 3 is equivalent to that of a second order underdamped system. Now what we're going to look and find is what is the relationship between these three case studies, and can they be equated to a second order system. Why is equating important? Because all the characteristics that we have learned, that is the calculations for omega n, damping ratio, the settling time, rise time, percentage overshoot, and peak time, they can only be done for a second order underdamped system. These are all only valid for a second order underdamped system. So when you have a system with three poles like case 1 and case 2, it's important to note whether these systems can function as a second order system. If they cannot function as a second order system, then we have no choice but to negate it as a third order or a fourth order system. So what we're going to do next is we're going to look at if we can generalize. So the question that we can is if or can we generalize a higher order system to a second order underdamped system. That's what we need to find out. Underdamped system. So in this case, you'll see that these two poles, P1 and P2, right? P1 comma P2 is called as the dominant poles. So for example, if you have -3 plus or minus 4j, -3, right, is called as the dominant pole. Okay, and the third pole, in this case case 1 and case 2, P3, right, P3 is referred to as the third pole. Now the rule states that when you take the ratio between the third pole and the dominant pole, if that ratio is greater than or equal to 5, then the system is equal to an underdamped second order system. This is the general rule that we have. So let's put this into practice. Let's look at a question that we have here. On page 188, we saw that we started with this discussion there. Now take an example of the three cases that we have, which is in example 4.8. So this is the three examples that we have. So if you have a look here, you can see that this first one, T1, this is a pure second order system, right? Now this one, that is T2, it's a third order system. How do we come to that conclusion? If you look at this, it's got two poles here, that is s square plus 4s plus 24.5 for 2, and it's got a third pole which is at minus 10, right? Now if you look at the T3, again it's a third order system that we have, and we see here that you have two poles, that is s square plus 4s plus 24.5 for 2, plus you have s plus 3 is equal to 0, which means that you have a third pole at minus 3, right? Now when we do the calculations, we can see that what are the roots of this equation and what are the dominant poles and what are the third pole, right? So that's what we need to first find out here.